Hi, I'm Boston Morman, and this is my recording for Oceanography and Meteorology, or Geology 3314. My presentation is on offshore wind farming and the engineering, economic, and environmental aspects. The research is very important due to how it affects marine life, but also being able to get natural energy and it not affect the environment with carbon emissions and depleting the ozone layer. So trying to be quick on this overview, offshore wind farming is basically just a group of wind turbines out in the ocean. They're placed in the water in order to harness wind, such as like the trade winds, very fast and good wind, and also to provide large-scale clean energy. It uses ideas from both oceanography and meteorology, very um, important in both aspects. Oceanography for the aspects of how the ocean is going to affect the turbines, the movement, the currents, all that in the meteorology in order to see, okay, we need wind, where's the wind at? And so that they're both very important, and using both ensures very safe and sustainable wind energy. And the overall purpose of this presentation is to explore the economic and environmental and engineering aspects of offshore wind farming, providing anybody who sees this with an understanding of offshore wind farming and its effects. A couple just small precursor information. I know this isn't a very beautiful tab. I don't need it to be. The wind farming in general gives renewable energy, so it is a way of trying to replace fossil fuels, giving us clean energy that doesn't affect the ozone and doesn't have carbon emissions. So it's clean energy and it is renewable energy. Wind depletion is a common issue where if there's not wind, you're not getting energy. They're very expensive to build. Offshore is even more expensive than onshore, but even onshore is expensive. And then again, both age. Both of them can have issues with erosion or just overall slowly mechanical pieces break or the blades of the wind turbines slowly stop working as well. And so aging is a major issue. This is a little kind of diagram of how it works. So the wind spins the blades of the wind turbine, and then in the wind turbine, there is a gearbox and a DFIG. The DFIG is a dually fueled induction generator, and that generator is what actually converts the mechanical like movement and heat and friction into actual movable electrical energy. And then outside of the wind turbine, you either have your transformers, which can take the energy and then put it into the power grid, or going through slip rings and then through substations and through other things, you can have a power converter that changes from AC, DC, DC, AC, and filters it, and then also gives you some measurements of the variabilities of what's going on, so that way you have a better understanding of how your wind turbines are doing. Some general information for the wind turbines. The offshore wind turbines, they're larger than onshore, being able, this is able to give us more energy production through them. The materials for the blade and aerodynamics is a very important engineering aspect because if they break down fast or if they are very heavy, they might not move as easily. So it's very integral to know what material would be best when building these turbines. Foundations is a major aspect. I have them listed there, and I'll come back to that in a couple of slides. Connection to the energy grid, of course, is also very important because you need to get the energy to the people. Expensive. It's also, again, very costly. And then last, I have some benefits here, job, energy, long term, both with jobs and with giving energy, and a couple other aspects of this give long term benefits. And it also helps other sectors such as welding, engineering, steel manufacturing, and even others. Here's another little diagram kind of showing the turbines use the cables to get to the substation. The substation is where the energy can be stored, can be depleted if you don't have enough if you don't have enough infrastructure to hold the energy, then it can also be depleted there. And then it also combines multiple smaller cables coming from the wind turbines into one sea cable in order to get it all the way to the land. Usually, you'll also have another substation on the land that can also deplete energy and do power conversion. And then you go straight to the transformer station after that. And that's to the energy grid. So that's just another kind of helpful thing to understand what this process actually looks like and the fact that you're not just engineering and building the turbines, you're looking at the substation, you're looking at these cables and burying the cables and getting them to the land. Engineering. So overall engineering, the turbines are larger, therefore requires more manpower, bigger machinery, and that brings the cost up. But it also an aspect different than onshore is the movement. Onshore, bringing them, whether it's by 18-wheeler or by train or however you're moving them, one, you probably have to transfer it from load to load to load in order to get it to your location. And it's very, very difficult to move them on land because of the corners you have to take and how massive and long the pieces are. Whereas offshore, even though they're larger, if you build them on the shore, you can just put them on a vessel and get them out to where they're being built. So it ends up actually creating a better environment for getting the pieces from the manufacturer to where it's being built. The next bullet I have here is about the pieces. So you have the tower, the nacelle, blades, the foundation, and the cables. So the three most visible and important parts is the tower, the nacelle, and the blades for general turbines. For offshore turbines, the foundation is also very important. So the tower is just, again, just the tower. It's just what it is built on, what puts it in the air. The blades are, of course, what spins. The foundation, excuse me, the foundation is just what it is built on to keep it afloat in the ocean. And then of course cables, run the cables, and then the nacelle is the basically the top part that the blades are spinning on, and it is where that gearbox and the um, DFIG is that actually creates the energy. And you have a cable coming from that through the tower down to the ocean floor all the way to the shore. So that's kind of the construction of it. Then materials and design, I mentioned a little bit about this earlier, but materials are very important because if your tower erodes or if it can't even hold its own weight, it's going to fall down. And then the design, the shape of the blades, the material of the blades can improve the efficiency and the durability of the overall turbine. Then the foundation, there are three main foundations: monopiles, jacket structures, and floating platforms, which I have a diagram for on, I believe, the next slide. The water depth, the depth of the water is also very important. This is mainly for the foundation, but also for the cabling and the amount of work it's going to take for basically swimmers or divers to get to the ocean floor to do what they need to do at the ocean floor. And then that goes along with energy transport, transporting the cables, getting the cables buried at the ocean floor. Here is three of those foundations. You've got the first one is a monopile, basically just bring the tower all the way down to the ocean floor, and then put it in the ocean floor. This is generally going to be close to the shore where you don't have to go that far down. Then the next one is the jacket structure, which is basically going to be three or four legged kind of truss structure attaching it to the floor with massive foundation piles. And then the last one is just a concrete cone, again, giving it a heavy base. It's less often seen, but it is still used. And then you also have many versions of floating platforms. So floating platforms are just what it is, a floating platform that has the turbine on top, and then it has cables that connect to the ocean floor that keep it, one, keep it from drifting and keep it in place, but also keep it upright. Next is building and maintenance. So building and maintenance, it requires the building, and this goes with engineering, but also economics. So the building can be very difficult. These are very big, and you're on the water where you got drifting, and so it requires specialized vehicles, vessels, heavy lift cranes, and a lot of careful planning. The maintenance also requires a lot because if they're not working, if the gears break down, if the blades wear, whatever's going on, you need to have people who understand how to fix that, and you need to get them there, and that can be very costly. One thing that helps limit that is remote monitoring systems, so that way instead of sending technicians out to figure out what's going on, you can just monitor it from where you are and then send them out when there is a problem that arises. And then I put a little bit of just straight econ on here, which is the cost. Slowly is decreasing. As you build the infrastructure, get more of these specialized vessels, get more of these heavy lifting cranes on these vessels, and understand better and have similar plans for different environments, then it makes it easier to build more. Now to just straight economics, I've got this graph over here, and I lost my paper. Sorry. This is from ResearchGate. So ResearchGate is the people who created this little graph over here, which describes some of the different aspects of the cost. So economics, it creates jobs and manufacturing, engineering, maintenance, a bunch of jobs. It improves energy independence from fossil fuels. The costs remain stable once built because you don't have to run fossil fuels to keep them running because they create energy and you can just use that energy to run like the substations and anything that requires energy. And then you also have it also just kind of remains stable from that point forward because you're not having to put too much extra money into it unless something breaks down. Then lastly, you have governments. This is a bad thing. You can't really get it going without government support. You need that high level of income and basically forced money in order to get it even started. And then a need for a bigger grid infrastructure is another kind of downside. Environmental impacts, there is positive and negatives. The positives is that it can create artificial reefs, and for the whole world, it reduces carbon emissions. But some of the negatives is construction noise can disorientate and disturb migration patterns of marine life. It disturbs the seabed, and turbines may affect the view from the shore. Here is a little image that kind of sums that up. If you want to pause and look at that, you can, but I'm running low on time. Physical oceanology, trying to draw it back to the course, starting with the kind of physical oceanography of how the water's moving and also like wind. Wind, of course, is what gets this going, and that is a major part. Oceanography has a lot with that. Meteorology has a ton to do with wind, so it's very good to have that. The whole process of building these starts with understanding the wave height, the period, the direction, what's going on. All of these different aspects help create an environment where you are able to um, yeah, where you're able to build these wind turbines. And then a biological um, oceanography. So artificial reefs create. So having these turbines create artificial reefs because they have hard substrate where you generally have softer soils. And this can create a complex ecological community, but it can also disturb migration patterns and marine mammals. In conclusion, offshore wind farming, very not just feasible, it's actually happen. There's a ton out there and can be very good. The foundations is a lot of what it takes looking into this. And then the cost, it is, of course, very expensive, but it does have some good for marine life and some bad for marine life. So that when you just look at it from a glance, you're like, that could hurt the marine life, but it kind of balances out. And then it gives good, consistent, renewable energy. Then this last tab has all my resources. So we have offshore wind power development in Europe. This article compares offshore and onshore wind energy systems. So that's kind of where like my precursor information and some of the comparisons I have mentioned has come from. Then there is environmental impact assessment framework for offshore wind energy development based on the marine good environmental status. This article goes through a process to assess the environment, and it also considers some construction and the phases of the operation of getting these built. Then the next one, the report over large scale offshore wind power in the United States. This focuses on the engineering and the building and has some a little bit of information in there about the like foundations. The next paper is ecological and economic cost benefit analysis of offshore wind energy. And this focuses on environmental and economic aspects of offshore wind projects. So it gives a lot of information about those. And then it kind of tries to balance the concerns and the cost feasibility and tries to balance the two out while kind of engineering a system. And then the last one is a chapter of a book that examines economic aspects and environmental aspects and tries to, again, balance the views of both. Mhm. And that is environmental impacts and economics of offshore wind energy. So this was my presentation. Thank you for watching.